So now we've established that consensus can be reached using the proof of work protocol. The question is, okay, so that's fine, but what guarantees that the database is consistent in the sense of that you can't change what happens in the past? Well, and this again is something that the proof of work protocol does, is because it creates economic incentives against cheating. So here's how this works. So suppose you have a blockchain here, and the block B2 links to the block B1 in its header. And so the first thing that the blockchain technology with proof of work protocol does is it has an incentive to support the longest possible chain. So here's how that is. So suppose for whatever reason there is two blocks that form simultaneously. Let's just take this as given. Block B3 and block B4 form, and then a new block B5 is brought up that links to block B4, and then there's a new one which links to block B6. Now the question is, would it be possible to link and add to block B3? So is it possible that the chain just splits and that we have that we create multiple realities? Now that would be bad because it would basically violate consistency. Now the issue here is that if you are a miner and you want to build and you have found a new block, right, where would you want to put it? So would you add it to B3 or would you add B7 after B6? Now the problem is if you add it to B3 and somebody else after you goes out and adds it to B6, then you lose your Coinbase reward. So all the work that you did is all for naught. So this is a very big incentive to stick with the longest chain. Now, is there a result for that? Is it actually an equilibrium? And the answer is yes. So there's two papers in the literature. One is by I cannot pronounce the names, but it's published in 2016 in a computer science journal, and it essentially says blockchain mining games gives a formal proof of the longest chain support is indeed an equilibrium. And there's a paper by Bruno Biais and co-authors in the Review of Financial Studies, which essentially shows the same result. Now, the next thing is, and this is the more interesting part, is can we be sure that you can't alter the past? So I've already explained the double spending problem. Right? Now, you can't forge signatures, right? But what you could do is you can if you are the owner of a particular item in block B2, right, which contains the transaction from Alice to Bob, then maybe, the transaction from Bob to Alice, Bob wants to reverse and instead say that Alice actually paid him the money. So basically double spend the amount of money. So how do you do that? Well, what he wants to do is he wants to rewrite the history starting with block B6. Right? So when you have a block B6, what he wants to do is he wants to add it to B1 and create an alternate reality, double spend, and therefore, spend the money twice. How could Bob do this? Well, to do this, he has to basically, because supporting the longest chain is an equilibrium, what he has to do is over time he has to build a block B6, B7, B8, B9, and B10 to outpace the existing blockchain. And the longer the chain gets, the harder this is to be done. So this is why one of the things that we observe in blockchains is once your transaction is sufficiently far down the chain, it becomes really difficult to alter. And that creates the security. So how could he do that? Well, he has to done repeated mining, right? So he has to be much faster, has to expend more resources than anybody else. Or, and this is the other part, he could also be, if he has the ability to be the proposer and therefore knows with certainty that he or she is able, so that if Bob knows that he is able to build a new block repeatedly, then he can also alter the past. Now, what prevents that from happening? Again, prevents that from happening is that it's really expensive. So Bob wants to build this extra alternative reality. How would he do that? He needs to be predictably able to add several blocks without interference. He needs to be faster than anybody else, or he needs to have the ability to reject new blocks that are added so that he can basically spend his own time and just at his leisure time build the new blocks until he's done. Now, the last part is, in order to be able to reject everything, is the so-called 51% attack, where you basically just go out and you can reject anything that is new. And because in the validation process, there's the majority rule is there. And so basically what you do is by having 50%, 1% of all the network nodes and all the power, you can just reject. So how does the proof of work protocol normally prevents this? Well, mining success is random. So therefore you do not have the ability to predictively be able to add blocks over time. Number one. And how is that? Why is that the issue? Well, it's also, you have to expense energy, and it's very expensive to do. In order to be doing that, now one thing you can do is you could do a so-called 51% attack on the network. Now I have this is older data actually, so I think this is from it's actually a year old now. So at the time you needed 25 million terahashes per second, which is the speed at which people can create these guesses to find the nonce. So now let's just do a back of the envelope calculation. The hash rate, therefore, is 25 terahashes per second. The best GPUs that money buys you at the time would create 25 gigahertz per card. So that's 0.025 terahashes per second. So what that means is you need 5 billion GPUs in order to create the hashing power, which is 21% of the network. One of these GPU costs you around $200. So the total amount that you need in order for this to work out is $1 trillion, or as Dr. Evil would say,
$100 billion. Gentlemen, silence.
Not even, close. All right, now, so is there actually any equilibrium? Do we actually have a theoretical result on that one, right? Now, here's an interesting result. So now the way we deal with these issues here as economists is we basically say, okay, fine. We're not saying that it can't be done. We just say it's very expensive. And so that gives us some indication of what the long run viability of the blockchain will be. So now one thing, that we've discussed that before, that is really all about the Bitcoin network, is that the Coinbase reward at some point goes to zero. So it means that mining a new block gives you no more payment. And what you need at that point in time is actually need transaction fees that are being paid to you. And so, then that means essentially in order to maintain the network, people will have to pay relatively high transaction fees. Number one. Number two, another observation that we saw over the last half year or so is that as the price of Bitcoin fell dramatically, the value of the Coinbase reward dropped also dramatically. So Bitcoin went from, I think, $15,000 to $3,000, means that the Coinbase reward that you get for every block dropped by 80%. Now, why is that relevant? Well, the electricity that people pay for running the blockchain does require you to use some real money. And so if the Bitcoins are no longer, if the reward is no longer big enough, then essentially what you do is you have to reduce your network power. Anyway, so here's an interesting thing. There's a colleague from, two colleagues from Queen's University have looked at this question and said, well, look, generally speaking, what has to hold an equilibrium is that the aggregate mining cost has to be equal to the aggregate mining reward. Otherwise, you would not want to, you can't have security in the blockchain. Now, if you want to have a double spending attack, what do you need to do? You need to expense resources, right? What you need to do is you need to win N blocks for which you actually receive a reward until you have the confirmation. And then you have the ability to also double spend. So you make money twice, essentially, when you do a double spending attack, which is you have to overtake the existing blockchain where you get all the rewards, and you also get to double spend. Now, the condition that would prevent that from happening is in a nice paper by Thorsten Köppel and his co-author, and essentially says the mining reward that you get multiplied with N is the number of block rewards that you need in order to believe that this is secure, times N plus 1 must be bigger than the amount that you get as a double spend. So this condition has to be satisfied in order to make sure that the blockchain is long run sustainable. And as the mining reward declines, or as the mining reward is less valuable, the possibility of a double spending attack goes up. Now, here's bigger insights though, and this is something that I want to bring up, is the major innovation of Bitcoin is essentially following. So what it does, it combines cryptography, the idea of a blockchain, and the proof of work protocol. Now, there were other applications of proof of work. There's something called Hashcash. And there were also applications of blockchains that were used in particular for timestamp servers when there was a central authority, but you had different servers all over the place with different timestamps. So in order to have consistency across the network. What had not been done is actually put these together. And this is essentially the major innovation of Bitcoin. So if you think that's not a main innovation, well, just think twice think of Tesla. Tesla did not invent the electric car. All that they did was put the right components together and create something that people found very desirable. Now, the philosophy here of Bitcoin is that anybody is allowed to write to the ledger, but we don't trust anybody. And the key requirement is, and this is in order for this to work, is you cannot be able to predict or determine when you will write again in the future. So you cannot manipulate or take it over. And what the proof of work protocol does is it creates the randomness by solving this hard problem, which can only be solved by random guesses. Now you can, of course, tilt the cards or tilt the deck to you by expensing more money than others, so then you're more likely to be the winner, but you can never be sure. But we also don't want to say that there's other alternatives that people are currently working on in order to create different consensus algorithms. And I'll be talking about them next.